So, welcome everyone. I'm going to tell you about, just very briefly, about a variety of projects that are going on in my group. I'm a theorist. What we do is we start with the basic physical laws, namely quantum mechanics, to understand how atoms interact, both in molecules and materials. And very recently, in the last couple of years, I've just decided that almost everything I do now, I want it to be related to this topic here. Okay, so I'm going to lead you through that. In particular, I'm going to have a couple of slides that talk about this issue that Fred introduced, which is the issues associated with combustion. You know, I think that in many ways, when people talk about new energy technologies, they often stop and say, combustion, oh, it sounds like a dirty word. The fact is that as Fred pointed out, combustion is going to be with us for a very long time. It's not something we have any choice about. We absolutely need to find ways to optimize engines and the molecules that make up the fuels in order to do this in such a way that we're burning more cleanly and also capturing the CO2, et cetera, all the things that Fred said, in addition to hopefully dealing with issues of our own national security by deriving our sources of fuels right here at home. So I have a project now that is part of this larger center that I have a couple of slides I'll tell you about. This center was the only center that was funded in the area of combustion in the entire nation, so we're very proud of that fact. We think we put together, I should say, Ed Law really put together a dream team, at least that's what the reviewers said, so I can say that, of people to work on this problem. And so I'll talk more about that very briefly. Pablo mentioned, I've been working for over a dozen years now looking at materials issues associated with the extreme conditions inside jet engines. In particular, these jet engines are not only used to power aircraft, of course, but they're also used in stationary power plants, different size modules, obviously. But the materials issues are precisely the same. What you see there is somewhere a pointer, but I don't see it. So I should have taken yours, Lynn.
It's right in your slide.
That's okay. 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 So, how did I miss it? Okay. Oh, I see. No, that's all right. Anyway, so what we've been doing is to try to understand the issues associated with how you protect these metal jet engine blades that operate actually at temperatures above their melting point. That should frighten all of you. You all take airplane trips, right? And these things are subject to the flame temperatures in these engines actually are above the melting point of the metal alloy that's used for these jet engine blades. How does that work? It works because they're protected by a ceramic coating, a very, very interesting ceramic coating. And we have been involved, multi-layer ceramic coating, we've been involved in understanding how to improve that coating so that one can operate at even higher temperatures and improve the fuel efficiency or improve thrust if that's your goal. For flying. Okay, another area that was recently funded, we've done a little bit of work related to this. This is a very nice picture of the experimental fusion reactor that is going up in Europe that the Princeton Plasma Physics Lab has been involved in. They inspired me to start thinking about some of the materials issues associated with containing the fusion plasma. There are really important issues, as you can imagine. The temperatures get very high. There are neutron fluxes that come out of the fusion plasma, such that we need to understand, and there's also the particular issue they're worried about that they asked me to think about has to do with tritium, which is a hydrogen isotope, getting into the metal that faces the plasma. So I'll talk about that very briefly. Another area that I won't talk about at all, I'll give you an example of what we do in this area and in this area, and the rest of it I'm not going to talk much about in the limited time available, but if you're interested, we can talk about it separately. Wally Soballejo, I stole this picture from him. He works on lightweight vehicles. I also work on lightweight vehicles. We're interested in developing metal alloys, aluminum and magnesium alloys that can be used for lightweight cars, for any vehicle you like, ships, airplanes, cars, et cetera. Obviously, that will improve their fuel efficiency. Another Energy Frontier Research Center that was just funded by the Department of Energy that I'm involved in, and also my colleague Miko Hataja is involved in, is looking at new materials for solid oxide fuel cells. The internal combustion engine is an incredibly efficient way of processing fuel. But another way that it has tremendous promise for generating electricity is by taking fuels and actually running them through a cell like this that actually has the potential to be able to use dirty fuels even without problems. And so this is another mechanism for generating electricity, either from hydrogen or from hydrocarbons. And then lastly, I'll just say that I just found out that another Department of Energy grant that I had pending was funded to develop new materials for photovoltaics, so for solar cells. And I have another one pending having to do with essentially doing what's called photocatalysis, which is to take sunlight and make liquid fuels. And hopefully that's going to get funded too. So these are all the areas that we're working in. And now I'll just spend a minute telling you, this slide is from one of my now collaborators, because he is part of the Energy Frontier Research Center. Bill Green at MIT put together this slide to just point out things that I don't even need to discuss in detail because Fred did such a good job already. But the point is we have to start thinking about a whole bunch of new fuels that are going to be coming online and how they operate, both understanding how to optimize their combustion chemistry and the fluid dynamics involved in the mixing of the chemistry and the thermodynamics with the fluid, with the gas, and how to then take that information to understand how to design new engines. There are a lot of new engine technologies that are being considered. They all have quite different regimes in terms of pressure and temperature that one needs to think about. And so this was the motivation really to go to the Department of Energy, Basic Energy Sciences, and say, we want to put together a team that goes all the way from molecules, which is where I live, all the way up to engines, to be able to optimize fuels and engines for clean combustion. And so that's what this is my little bit here, from molecules to engines. We have, so I should say the Department of Energy put out a call for proposals. They received 261 proposals. They funded 46 proposals. We're the only one funded on combustion. And Ed Law, who unfortunately is not here, he's the director. He suckered me into being the co-director. And we don't yet know who the associate director will be. There are 15 people involved, including Fred and Yiguang Zhu, who's listed here. Yiguang's on the steering committee. Bill Green I already introduced. There's people here from Sandia Combustion Research Facility, which is out in California, who are experts, and then also experts from other universities, as well as also someone from Argonne National Labs. And the idea is that all of us together are going to cover these areas of expertise, both theory and experiment, chemistry, flames in terms of the fluid dynamics, and also engine design. And so this is really nascent. The money is not here yet. Okay, so we're just starting to think about how to put this together, and we're all very excited about it. So, do I have a minute or not? Am I done? Should I be done? Okay, I'll just do this one slide then. So I hate it when people go over, and I don't want to be a hypocrite. So anyway, this is just one example of the kinds of things we do in terms of materials. So we are interested right now in the material tungsten, which is the prototype for one of the interior portions of this fusion reactor. And there are good reasons why one might want to use tungsten. You remember tungsten is actually what's the filament inside your light bulb, and it happens to be able to exist at very high temperatures, and that's a good thing. It has a high melting point. Also, it's a good neutron absorber. And the question that Princeton Plasma Physics Lab posed to me was, how easily does it incorporate hydrogen or its isotopes? Because it's going to get bombarded with those materials, and we're very concerned about that because hydrogen in metals often causes problems. Okay, it's an actor in corrosion, and so we've actually looked at this now, and we haven't actually looked at the problem of a neutron hitting metals, but we know that when neutrons hit metals, they knock atoms out of place. They form vacancies. Missing atoms are there. That's what this is supposed to mean. And it turns out that hydrogen loves those vacancies. They just go straight to the vacancies, and they live, many of them, live. That should have been an atom right there, and hydrogen, up to 6 hydrogen atoms can collect around those vacancies. And when you have that many hydrogen atoms, what we are able to do is calculate essentially what we call an embrittlement function. When you gather that much hydrogen together, it essentially makes the material crack and blister. And so we made some predictions about how likely that happens as a function of temperature, which could be very useful in trying to understand how to look to optimize a tungsten alloy that will inhibit hydrogen incorporation. We've already done that kind of thing for steel. So with that, I'm going to skip all the thermal barrier coating work and just say, and thank Don Johnson, whose work I had a chance to talk about. And Don is somewhere in this picture. Where is he? He's right there. Okay. And so with that, and so I should thank the Princeton Plasma Physics Lab and also Princeton School of Engineering. They jointly funded this small project having to do with hydrogen and tungsten. So with that, I thank you for your attention.
I'm really speaking not just for myself, but for Professor Ju, who's in the back of the audience here, and Professor Law, and Professor Sokolow, all of whom are part of the Thermal Sciences group in Mechanical and Aerospace Engineering. Let's see if I can. I want to emphasize the issue that we're most interested in is the idea of trying to reduce carbon emissions in net cycle over the next period of time. And you can see that we're talking about reductions here that are in the order of very large numbers in comparison to present CO emissions. In particular, the issue of transport and carbon emissions from transportation systems are thought to be one of the most difficult areas to deal with. And it's partly because of the size of the amount of energy that's being fluxed through the transportation system, as well as its source, which is principally petroleum. As such, we have to worry about backward compatibility for very large amounts of capital investment in terms of transportation systems, and also forward design issues. As we look at those issues, we can see that we want to keep some compatibility with the existing processing issues of petroleum. And what I want to emphasize is 2 points here. One is as we go from Saudi Arabian petroleum to the kinds of things we'll be using for petroleum in the future, the amount of energy processing requirement becomes very severe, principally because of hydrogen content in these fuels and the hydrogen upgrading necessary to shift the amount of hydrogen in the system towards what we want to use in real systems. This introduces a whole series of areas for producing hydrogen that are very important, but I think everyone now agrees that biomass is going to be a key to addressing these climate issues. The difficulty is that if we look at all of the renewable resources, including biomass, those numbers do not compare well with the total amount of energy production that we really require. For us as well, we have a very large amount of coal that's being used in electricity, and we know that China is going to increase its use in this area as well. So how do we deal with this? Well, there's at least 2 ways to process biomass. This is representative of one. I grow materials that have very high oil content. I extract the oil. I process the oil. And now you'll notice no oxygen in these systems. These are not the typical kinds of ethanol things that you and I are used to. They are now fully hydrocarbon compatible with petroleum products, as you see here on the left. I want to note one other thing here that's very important. These are the kinds of properties that are used to define what I put in a jet engine. If I go to a gasoline station and I collect gasoline today, tomorrow it's not the same. Next December, it's not the same at all. And if I do that in Asia or I do that here, it's very different. The question is how do I integrate these alternative fuels into those kind of problems? And this is why I need very strong compatibility. Now, why is this important? Because in comparison to kerosene derived from petroleum, this is the used CO2 emission that would have come from burning petroleum. But if I use any of these other oils, that use CO2 emission is replaced by the fact I photosynthetically captured the CO2 from the atmosphere. The problem is, each one of these oils represents only about 40% of the mass of the biomaterial I grew, and the biomaterial that I'm using is very resource limited. So the amount of fuel replacement that I can get is very limited this way. Can I use it better another way? This is the other way. Not only can I use it better, but I can also develop ways of using coal. You've all seen the clean coal ads recently. It really is clean. The idea is to use photosynthetic sequestration of CO2 from the atmosphere to displace the CO2 that's going to be present in the fuel when it is burned. I'm going to combine it with coal. I'm going to generate a liquid fuel. I'm going to simultaneously generate electricity. So I'm replacing both the electrical generation market and the transportation fuel market simultaneously. The co-production of fuels and power turn out to achieve extremely good optimal economics with very good solutions of many of the environmental problems. Important here is that I can also eliminate very large amounts of the nanoparticle emissions that occur from pulverized coal firing by replacing it with gasification as the means of making my gasified streams. In order to do synthetic fuel conversion, I need to remove sulfur, so I end up with very low sulfur fuels this way. In addition, I'm going to process some of the synthetic gases to power right on site. And you'll notice I've got two routes to that, one this way, one that way, that I can also use liquid fuels with it. This is to balance the two processes. So oxygen firing of such a gasification system also produces a CO2 stream, which is very pure in its process, can be dried easily, can be compressed, and can be carbon sequestered and stored. That's the key to this technology. How big of an advantage is this? As I showed you here, we got about an 85% reduction in C emissions. If I do this purely with biomass in this problem, bio to liquids plus electricity, I get a minus 22% carbon reduction in comparison to petroleum. If I do this with 38% biomass with coal, I get a 0 net carbon cycle out of this process. I'd be happy to share more about the economics of this. This comes from an analysis with my colleagues, Bob Williams, Eric Larson, and the Princeton Environmental Institute here. So you can see that if I use one of these processes of CBTL, coal plus biomass to liquids with full recycle, carbon capture and storage, or once through, I can generate very good economic solutions to this problem. Turns out not the one that produces most liquid fuel is the best. This is. It's called systems analysis. I need to know a lot about heat rejection in these systems and its quality to pick that one. Okay, well, now what's the problem? This all looks very simple. The problem is this is what the molecular weight distribution looks like in any of the fuels we use for transportation. And we don't know how all of those little molecular weight distributions change every time I make an alternative fuel. I need to find ways of compatibility between alternative fuels and petroleum so I don't disrupt the distribution or storage or utility in any of these systems. So these are the questions that need to be answered, and these are the questions that the Thermal Sciences Group are addressing. We have a number of projects, and I'll try to keep everybody online here. We have a project called the Carbon Mitigation Initiative that's directed out of PEI, which Steve Picala and Rob Sokolow are the PIs. It's funded by BP and Ford. We have a next generation aircraft fuel project looking specifically at this problem for aircraft fuels and for producing very low net carbon emissions and particulates. That's PI'd by me and involves the people you'll note here, all at Princeton. We have a Air Force MURI program, which involves a number of other institutions and PEI as well. And we are looking at how to model real fuels with what are called surrogate mixtures of small numbers of molecules. A similar program involves Professor Law. That's stationed on the West Coast, PI'd by Professor Agapopoulos at USC. You'll notice another set of industries, and you'll note who's funding this. Air Force is a big player in this area. And finally, we have hydrogen combustion in gas turbines. This is an issue with the syngas power generation problem and controlling emissions. We've been working with Nettle and also Siemens. And finally, just recently, we have gotten an Energy Frontiers Research Center award from Basic Energy Sciences, which Emily will tell you a little bit more about. So this gives you a kind of a broad picture of what thermal sciences is involved in here. We work on the fire safety aspects of this, on the fuel property aspects, and you'll notice the kinds of things you're talking about in terms of real-time sensing are very important for control of these kinds of systems. Thank you.
As Pablo mentioned, I'm entrepreneur in residence here. One of my functions is to meet with faculty and students about ideas for starting new companies or spinning off technologies. And I've enjoyed that part of my being here. But let me start off with what I see the purpose of this meeting is. First of all, does this make sense? Now to me it makes a lot of sense, but I'd rather hear that from you than my own thoughts. Give you an opportunity to see what faculty are working on here. Faculty can see what the local companies are doing. It's a lot better to meet and interact and have coffee, and we have a reception afterwards rather than just read about stuff in newspapers and trade journals. And of course is to determine what the next steps are. How do we go forward from here? So after this meeting we'll kind of make some notes, distribute them, and go to Plan B. A little bit of history. Princeton's had a number of really successful industrial academic interactions. And I just put 3 of them up here, but there are many more. These are the ones I've been involved with. About 20 years ago, there was a POEM, Center for Photonics and Optoelectronic Materials. Jim Sturm was heavily involved in creating that. PRISM, that sort of morphed into Princeton, which combined materials with the optoelectronics. And then finally, most recently, we have MIRTH with Prof. Claire Gamakel, and I'm not going to steal her thunder. I'll let her tell you about it, but that's also been a very successful industrial interaction. Just to give you my personal interaction, my history with Princeton and these types of academic interactions. I've had 2 startup companies, one Epitax in 1984, and the second one is called Sensors Unlimited. Epitax was more fiber optics, Sensors Unlimited was fiber optics and also infrared imaging. I got involved with Steve Forrest, who was on the faculty. He joined in 1992. About the same time, Marshall Cohen and I started Sensors Unlimited. And it was really a synergistic thing. And POEM, which was then the Industrial Affiliates Center, really provided the nucleus for us to interact. Steve was coming in. He needed to set up his equipment, get his students going. We were starting a company. We had engineers, but we didn't have a lot of equipment and facilities. So via joint R&D programs, we were able to share these things, and both really benefited from them. Lots of student jobs, not only summer jobs. I think at Census we probably hired maybe close to 10 Princeton graduates. We licensed patents. It was just a really nice interaction. Between these two companies, net, there was over $1 billion in sale. Over 1,000 jobs were created. And one of the best part is we were able to pay back over $100 million to the government in the form of corporate and payroll taxes. So it was really a win-win-win for everybody. And I give a lot of the credit for both of these companies to the centers that existed at Princeton University. So what I'm trying to do is to tell you it's really worked for me, and it can work for you too by getting involved with the university. As I said, it's been a great deal for everybody. Again, the Mirth Center, I'm going to let Prof. Gamakal tell you more about that. But they've attracted companies from all over the United States that participate in it. In fact, I was down at a trade show called Clio last week in Baltimore, and I see they had their own booth at a trade show. So, it's really been an active organization and really gets out and interacts with the world. Now, if I was an industrial member, if I hadn't been involved in these things, I might say, well, how can a university help me? And, just a couple, I think you're going to find out by listening to these talks. But I think one of the best ways is by joint funding programs. My companies have used the SBIR system, Small Business Innovation Research. It's a funding system the government has for small businesses. But now with the stimulus program, there's a lot of other things going on with the Department of Energy, most recently these ARPA-E programs, but there are going to be more as the stimulus stuff evolves. And many, many of these programs either encourage or require companies to interact, to have universities on their programs, and vice versa, for universities to go out and find industrial participation. So I think the stimulus program is, just one of many ways that this can interact. At first glance, nanotechnologies and lasers, what does that have to do with me? Well, that may sound a little foreign to you or a little bit up in the clouds, but when you get into pollution monitoring and gas sensing, then it's not so far removed, because I think a lot of you deal with things like that. Let's turn it around. How can companies help universities? Just make them aware of the problems you have. An outlet for technology. There's a lot of great technology here, and if you get to talk to the people, this is how you'll find out. I can tell you from my own experience, Princeton's very easy to work with. John Ritter, in terms of licensing, he's a deal maker. And you won't sit there for tens of meetings or get to the point. And we've worked with them for over 20 years, and we found not just John but the whole university to be really easy and friendly to work with. So I think that's the end of my comments. I think next on the schedule is supposed to be the funding lady, Paula Durand. I don't see her here yet, so I think what we'll do is maybe start on, if you don't mind starting a little early, Claire, get on with that part of it, and when Paula comes in, we'll just have her talk about the funding programs available for the state.
Okay. Well, good afternoon. Figuring that I had 10 minutes, I figured I would focus on one example to tell you one specific aspect of our work on organic solar cells. Before I did that, I thought it was important for me to share with you some statistics. So I gathered this information. And so if you've seen this, bear with me for a couple of moments here. So if you look at the global population stands at about 6.4 million people. And of those 6.4 million people, about 300 million reside in the United States. That makes it 5% of the global population. Now, if you ask the question of how much energy we consume, the global energy consumption stands at about 460 quadrillion BTUs. That's British thermal units. And quadrillion is 10 to the 15. Of those 460 quadrillion BTUs, about 100 quadrillion BTUs is being consumed in the United States. Okay? Those are all big numbers. So what do these big numbers mean? If you take these numbers, divide by the population, and then divide by the number of days there are in a year, and then divide by, let's say, the energy density of gasoline, what you get out is that the world consumes energy equivalent to 1.5 gallons of gasoline per person per day. And the United States then consume energy equivalent to 7.5 gallons of gasoline per person per day. So this is quite an alarmingly large number, considering that we probably don't even drink a gallon of water per person per day, okay? And from this number, you'd gather that, yeah, I mean, there is an imminent need for us to find renewable energy that is A, sustainable, B, has negligible impact on the environment. And that's why we look towards the sun. So I'm showing you here the spectral irradiance of the sun. Okay, the solar radiance is at 1 kilowatt per meter squared. And if you take those units, what this means is the annual sunlight gives energy at about 3.6 million quadrillion BTUs. If you do that same kind of analysis, what this means is if we can effectively and efficiently harness solar energy for an hour, that's enough to power human activity across the globe for an entire year. Hence, this motivation and this drive for solar energy and solar research. So solar cells are used to convert sunlight to electrical energy. First-gen solar cells are these single crystalline type silicon devices. The thermodynamic efficiency, so this is the maximum achievable efficiency that these devices can hit, is about 33%. In the lab, they've been demonstrated to be between 20 to 25%. Now, if you incorporate them as modules and you put them on roofs, their efficiency drops a little bit, so it's about 18%. The biggest problem with these first-generation solar cells is the cost. Okay? They're way too expensive compared to coal. So there's this next generation or second generation solar cells. These are thin film devices, so they're polycrystalline. That drops the cost significantly, but here you take a hit in the efficiency as well. The materials that are used to make these thin film devices are cadmium, telluride, for example. They're rare earth metals. They could be toxic. And so we wanted to ask a different question. So I'm plotting here efficiency as a function of cost, reminding you that Gen 1 solar cells are right about here. Gen 2 solar cells are right here, so these are the thin film devices. Gen 3 devices we didn't talk about. These are the ones with fancier architecture, and so they're more expensive, but they're also more efficient. What the organic electronics community is asking is whether we can target right about there. We take a hit in efficiency, but we can dramatically lower costs. Indeed, market analysis that's been done has shown that if we can make about 10% efficient devices, we're in business, okay? So that's the question we want to ask. Just quickly, let me show you how an organic solar cell is built and how it works. So here you typically start out with a glass or a plastic substrate, okay? You have a transparent anode, and then you put down your organic layers. You need an organic electron donor, and you need an electron acceptor. And then you put on your cathode. So here are energy levels that are associated with the donor and the acceptor. So this is the LUMO level and the HOMO level, or the conduction band and the valence band. And so when you shine light, light gets absorbed in the donor, and then you generate an exciton. This is a tightly bound electron and hole pair. The electron then shifts to the LUMO level, and the hole remains in the HOMO level, and these get collected at the external electrodes. So solar cells are inherently not very efficient devices. Organic solar cells especially are not very efficient. The highest efficiency that's been reported a couple years ago is about 6%. Okay? And you can begin to understand why that is the case. The efficiency that's associated with a device is a compound of all these different efficiencies. So if you have one single step that's not efficient, that sort of propagates onwards. To characterize these devices, you plot the current density as a function of voltage, and you get a diode curve, and it's really the area here that's below the zero line that gives you how efficient your device is. The bigger the area, the better your devices are. Now, I'd like to call your attention back to how these devices are made. You'll notice that these devices are often built from the bottom up. Okay? You put down one layer, and then you put down the second layer, you put down the third layer. And that's because, I mean, we're following what's been established for the silicon industry. But organic is a completely different beast. They're frequently mechanically and chemically fragile. And so if you're using the same technologies to put down and pattern the cathode, for example, on the organic layers, you can potentially damage the organic layers. And so what we'd like to focus on is come up with non-invasive processing technologies to make these devices. So here in this example, I'm showing you how we can laminate to make organic devices. So the idea here is as follows. You want to make these devices separately, okay, the different components separately. And then in one final step, you bring them together. So in this example, we've basically patterned and deposited electrodes separate from the active layer. Here we're using polydimethylsiloxane. This is silicone. This has the same chemical structure as the RTV that you use to caulk your bathtub. You can pattern and deposit your electrodes without harming the photoactive layer. And then when you're ready, you laminate to make contact. Now, there are several merits associated with this lamination procedure. First of all, you have this modular construction of devices, so you can individually optimize the different layers. Second of all, you have custom engineering of the interfaces. So I've mentioned that charge extraction is a problem. You can imagine putting down chemical species here that can enhance charge extraction. And this is something that you can't easily do when you're building things from the bottom up. Finally, you can imagine doing this over large areas. And if you do this over a large area, it can potentially enhance fast throughput combinatorial testing of new materials. So we're working with a chemist right now who's going to synthesize a bunch of these new materials, and so we can inkjet print them down and laminate and test them really quickly combinatorially. So I wanted to show some data. So here are current density plotted against voltage for different contacts that we've made to the same photoactive layer. So we're putting down one contact, we're taking it off, we're putting down a second one, and then we're taking it off and we're putting down a third one. The point of this graph is to show you that this technique is actually really robust. It does not depend on the contact that you're making. What you're testing really is the characteristics of the photoactive layer. Now looking to the future, how scalable is this process? We believe this process is scalable and it's compatible to roll-to-roll processing. So these are processing technologies that have been developed and established for the newspaper industry, for magazines and whatnot. And if you take potato chip bags, for example, where they're depositing aluminum, and these are the specifications for depositing aluminum, if you use those specifications as a benchmark, you only really need about 100 machines to operate for a year to make 10% efficient solar cells. Now, of course, I'm not saying that organic solar is the way to go, but using the sun is clearly going to be one of the ways, and we think this is a good way to move forward. Oh. So just to show you that printing is possible, so these aren't solar cells, but these are sort of backplanes for displays that we've printed using sort of similar technologies.
So I'd like to spend the next few minutes telling you a little bit about the Andlinger Center and some of the logistics about this meeting. The Andlinger Center, as many of you may know, was established in July of 2008, thanks to an extraordinary gift from Princeton alumnus and international business leader Gerhard Andlinger. The center has 3 core areas of research. So we would like the center to support a vibrant research and teaching program with a focus on 3 things: developing new alternative energy sources, improving the efficiency of devices that consume and generate energy today, and inventing and improving carbon capture and storage techniques that will enhance our ability to reduce the amount of CO2 entering the atmosphere. So these are 3 broad themes. The center aims at pursuing these studies closely with scientists and policy analysts across the university. And this is very important, with an eye towards translating fundamental knowledge into practical solutions. This is built into the core mission of the center. We envision the center to be located in what we call a neighborhood, energy and environment neighborhood, which will comprise the E-wing of the engineering school, Bowen Hall, which is where the Prism Center stands, and the Carfield Center, which will move across the street, whereas we intend to have a very nice conference center in that location associated with the Anlinger Center. And there will be, very importantly, a state-of-the-art facility. A major theme will be, within the center, will be to bring together the finest minds in energy and environmental science with those who work on new materials. This was a strategic choice that Princeton made to capitalize on an existing strength. For example, to develop flexible solar panels or to develop heat resistance coatings that will enable power plants to operate more efficiently. And you're going to hear about both of these themes today. So accordingly, the new center will host a state-of-the-art facility, a shared facility that will have state-of-the-art imaging and nanofabrication facilities in addition to individual investigator labs. Because of the focus on translating fundamental knowledge into practical solutions, close interactions with industry will be, from day one, fundamental to the existence of the center. And planning for the new building therefore includes space for industrial collaboration laboratories, as well as for hosting industrial visitors for extended periods of time. We selected the architects in January, Todd Williams and Bill Itzine, a New York-based firm, and we're in the middle of the design process for the center. The search committee has identified a candidate for the director of the center, and we're now in the middle of negotiations, trying to attract this person to Princeton. So we're very excited. We're sort of in the quiet but very active phase. A lot of things are happening. Speaking about the director, in going with the theme of the importance of industrial contacts, the director will consult with 2 external advisory boards. One will be focused on scientific issues and will be primarily but not exclusively academic. And the other board will be focused on strategic and policy concerns and will be mostly composed of people from industry. In addition, the director will oversee the recruiting of new faculty to the center, will oversee the development of the energy and environment neighborhood, provide leadership of research, educational, and outreach activities, and also, very importantly, allocate a non-trivial amount of funds for innovative research internally at Princeton. So today's meeting is the first of what we hope to be many meetings. And when we thought about the format, of course, we didn't know what sort of response we would get. We got a very good response. And so we have to cram everyone into just 10 minutes. So the format will be talks. We have 2 coffee breaks and a reception for people to mingle and follow up. We want the industrialists to hear about the exciting research going on here and programs that exist. And we want the academics to hear about the needs and interests in industry. And hopefully the 2 coffee breaks and the reception will allow for plenty of opportunity for people to talk. If time allows and we're doing okay with the timing, right before the reception we'll also have a little bit of open discussion. But if you don't have enough of structured discussion, please be proactive. Contact the faculty members, or the faculty members contact the industrial members whose presentations you're interested in, and be aware that this is just the first of many forums that we intend to organize. This is all I wanted to say, so it gives me great pleasure to introduce Greg Olson, who's my partner in crime in organizing this. Greg is a lecturer in the Electrical Engineering Department, and of course is president and founder of GHO Ventures. Jeff?
Thank you.
I can use this. It's all right. It's okay. This is fine. No, this is fine. All right. As Greg said, I'm a senior venture officer with the New Jersey Economic Development Authority. I specialize in clean technology on the technology and life sciences team. We have a couple of people specializing in certain other areas, and since I came on board about 2 years ago, this was my specialty, and have been working to fund companies in this area and also create programs to address this segment of the industry. So for those who are not familiar with the Economic Development Authority, we're an independent state agency. We like to say that if the government shuts down, we're still operating because we're not under a line item budget. Oh, okay, fine. All right. These are the areas we cover: financing assistance, access to small business services, real estate development. For those who've driven along Route 1, if you've seen where Chubb Institute is, we actually own an incubator for life science companies. And recently, we actually took commerce into the Economic Development Agency. And so we have an international trade area, which is interesting because before where I was or have been focusing on New Jersey companies and attracting companies outside New Jersey to the state, I'm actually now meeting with a lot of international companies who are really interested in moving to New Jersey or investing in companies in New Jersey. So actually, Israel is very high among states, countries that are looking to invest in clean tech companies here, but also China. So those are the two countries I've been meeting with. So there is a life cycle of companies that we fund, and a lot of people become confused as far as what does the Economic Development Agency do versus other state agencies. So this is a little chart that I actually put together this morning just to kind of show the progression. There's the New Jersey Commission on Science and Technology, and that really funds very basic research and development projects. As you move along the curve, we have an Edison Innovation Suite of programs. Those are the programs that I represent. And the reason why we have a specialized team is our partners are primarily the venture capital firms, the angel investors, there's equity funds. And so these are the companies that are startups primarily. They don't have revenues, there's losses. And they really require a specialized team and specialized type of financing. Versus the more traditional mature companies, and there's a group at the Economic Development Agency, and those are the traditional companies and where they look for 2-year profitable history. You can imagine that those are the companies that really partner with our commercial banks. So we like to say that we have financing that goes from the very, very early prototype stage, and then we move forward to very advanced and larger companies. But we are there to support the technology industry, and especially clean technology. And the focus here is really what we're doing to really support that in the state. And so there's a New Jersey Energy Master Plan. It was released in October 2008. It's supposed to be updated every 3 years. I think it was quite a long time before this one came out. But it does list a series of goals, and that provides a blueprint for our programs that we are creating in order to support these goals. And the goals are listed there, and you can see we're looking to achieve 30% of the state's electricity needs from renewable sources by 2020. And in order to do that, we have to really be much more aggressive in rolling out programs to really service this community, and that's what we're doing now. The last bullet point is important only because the investing in innovative clean energy technologies and businesses is really the focus of what the Economic Development Agency is doing at this time, because we really take that policy and we implement it in action. And so, as you can see, these are some of the goals of the Energy Master Plan and how it affects the Economic Development Agency, because our role is really to expand the current suite of programs that when I looked at it 2 years ago when I came in, and I thought this really doesn't address the needs of the clean tech community, because the maximum that any one clean tech company could get would be $1 million, and $1 million doesn't go a long way for a lot of capital expenditures. And so I spent a lot of time looking at other states, calling companies in other states, and saying, what can we do to really bring New Jersey to the forefront and bring it to where it should be? So when people talk about California and how innovative it is, they're going to start talking about New Jersey. And I think we've done that because about 3 weeks ago, the firm that is employed by the California Regulatory Commission called us, or actually called me, and said, I was reading about your programs and I think they're very innovative, and could you assist us in creating a solar incentive program for California? Which I then said that I work for New Jersey and I wasn't really ready to move, but it was a couple years ago, we probably would never have received that phone call. And so it's really encouraging that we are coming along the curve. And so where is this funding coming from? It definitely can't come from the Economic Development Agency because like many of the banking functions, we've been impacted by companies that are not paying us back on our regular amortization schedules, and we've had to stretch repayments out, and therefore, as income goes down, we don't have as much money to support clean energy programs. So the question is where will we get them? The first program that's actually out there, the Clean Energy Manufacturing Fund program to support renewable energy manufacturers, is coming from the BPUs, the Board of Public Utilities, our regulator in the state, the Clean Energy Program Fund, and that's from the societal benefit charge that everyone pays into the local utilities. It then is funded into the Board of Public Utilities, and it's used to create energy efficiency and renewable energy programs. It's from that pot of funds that I created the Clean Energy Manufacturing Fund. But we have a couple of other pools that have come in. From the Regional Greenhouse Gas Initiative, which is the cooperative state effort that New Jersey is part of to cap our greenhouse gas emissions. We do have a pool of funding coming in for that, and it's about 30 to 35 million per year, and we are mandated to use that to roll out new programs. There's the Retail Margin Fund, which is legislation that was recently passed in March 2009. To support combined heat and power, and then there's the federal stimulus funds that everyone seems to be chasing, but in reality, our part of it that we're rolling out into programs is not a lot. It's only 15 million out of about 74 million that's allocated to New Jersey. And so I wanted to put this in perspective, and I just want to say that some of these went to our EDA board today, so it's really hot off the press, May 12th. And there's a 10-day waiting period for the governor to approve these programs. So until it's really officially approved, I can't go into all the details, but I can at least highlight for you what they are. The first one is the Edison Innovation Clean Energy Manufacturing Fund. Actually, that was approved last year. There's 24 million supported from the Board of Public Utilities for that. We had one solicitation already at the beginning of the year, and we've opened up another solicitation that as of June 1st. So within the month, the state will be announcing who the winners are of the first solicitation. But there's still quite a lot of funding available for the second one. So if you are a clean energy or energy efficiency manufacturer and you can meet what we call Class 1, according to the Board of Public Utilities, which is photovoltaics, wind, tidal, and some other technologies out there, then this is a pool of funding I would encourage you to apply for. The window actually ends July 14th for anyone in this room who's thinking of applying. The second one is, it's called Clean Energy Solutions Capital Investment Loan Grant Program. I'm not sure why everyone has to come up with these long names, because I think it's just a tongue twister, really, for the fact that these are funds that are coming from the Regional Greenhouse Gas Initiative to support end-use energy efficiency projects. And there's going to be about 36 million available. And this program is very important for companies to note, will be online as of Monday. And so therefore, and I'll go into the particulars, you'll see that 36 million is not going to be a lot, and it's a first come, first served type of program. So if you think that you may qualify, I would say check the website and apply as soon as possible. I can go through some of the particulars in a couple of the next slides. This other one was just approved this morning at the board, the Edison Innovation Projects Program. That's from the federal stimulus program funding. It's only $15 million. I say only 15 because each project can go up to 5 million. So there's not going to be a lot of funding for this, but it's going to cover the whole array of renewable energy, energy efficiency. It's going to be for biomass. It's going to be for energy storage. It could be for combined heat and power, and also alternative fuels. So I wanted to let you know that again, there's a 10-day waiting period, so I won't go through the whole highlights of this, but it's really primarily for those companies that have a proof of concept. It's not for the very early stage. And then the Research and Development Fund wraparound is something that accompanies the research and development grants that are available. There's 15 million available this year. And yeah, okay, 2 minutes. Wanted to mention that. And then there's the Combined Heat and Power Program. And then that's from our Retail Margin Fund. $60 million is available for this. And this will really launch us into some really massive waste to energy type of projects. This is the Clean Energy Manufacturing Fund. 3.3 million in grants and interest rate free loans are available for this. And as I said, the solicitation began June 1st. And then this is the program that it will be launched on Monday from the proceeds from the Cap and Trade program. And these are the categories of fund uses. So if you're installing equipment for combined heat and power for end-use energy efficiency projects, and that does include solar, state-of-the-art projects, and innovative carbon emission abatement technologies, this would apply. I would mention that for any type of solar installations, they've modified it so that if this is a grant and zero interest rate program up to $5 million, but for those that are solar projects, because it's heavily incentivized, it's going to be loan only, and it could be repaid from solar renewable energy certificates. So these are the guidelines that will be introduced on the website on Monday. 1 million is the minimum, a very attractive interest rate. You're not going to get that in the private sector. And long repayment period, as you can see, up to 20 years. And the reason why I think this will go fast is because institutional is in there. So there's a lot of hospitals that want to do combined heat and power projects, among other type of entities. So this is the 866 number, but a lot of people know me in the room, and I have no problem sitting down, going through your requirements, and assisting you as you move forward. Thank you.
Okay, we're going to take a 10-minute